Hi, I'm Darren Corn. This is my submission for my Triple 120 Capstone project, making a automation for a water pump. So here we have here we have essentially we were tasked with creating two designs, and then based on stakeholder values and wants, we chose between the two designs and built that one and simulated it in digital with logic and flip-flops. So based on the stakeholders' needs and wants, the winning design was design 2. Um, we have a few assumptions. They are similar to design 1, but there's also some additions like that if R and F are asserted at the same time, the pool fills up at essentially a turbo speed. And I'll get to all the things here. So here we have our state diagram we have 8 different states using 3 flip-flops to achieve these 8 different states. The first state, S0, is idle, and these count down from 0 to 7 in binary. And when the idle is happening, so when neither V or L are on, R and F are both 0. State 1, our next state, will be the slow fill, so where just R is on and F is off. State 2 is fast fill, when R is off and just F is asserted. S3 and S4 are similar but slightly different, so they both are check the 2 clocks, because in our restrictions we have it where F can only be asserted every 2 clock cycles for V. So if V is on for more than 2 clock cycles, F can't be asserted with V. So that was our one caveat, and so that's why we have these 2 states here to measure when those clock cycles are up. So one clock cycle is checking that first clock cycle to when, or that second clock cycle for F being on, and that is actually not our S3, that's our S4. So as you can see here, we go essentially from S2 then to S4 here, and S4 has the output of 1, so it's the same output as S2, but then once we move on from S4, we go back to S3, which then gives us an output of R. So essentially when V is asserted for more than 2 clock cycles, I made the assumption that R would turn on as opposed to F, because obviously the pool still needs to be filled, but we can't use F to do it, so we have to use R. And then the changes I made for this design was I added a turbo speed. So essentially if S3 happens, and so the pool obviously needs more water, and after S3, if it still says it needs more water, well then I think it's safe to assume it obviously needs more water. So we turn on both outputs R and F and go turbo speed, essentially 1.5 times faster than R normally produces for 2 clock cycles. And I do 2 clock cycles because I wanted to include a failsafe here. As you can see in S7, S7 is the failsafe, essentially checking after about 4 clock cycles if V has been on, if V is equal to 1 for 4 clock cycles, it makes it to S7, and if it ever makes it to S7, afterwards S7 will just turn off R and F, just independent of what V and L are equal to. R and F just get overwritten and automatically turn into their off states. And that's just to ensure that if the sensors that I have no control over so V and L, if those are bugged, broken, glitching, this design will ensure that we turn off the pumps, because if V is on for more than, if we're filling this pool up really, really fast, and this can be adjustable by adding more states and more checks, but for just a precautionary measure, I set the clock state to be equal to 4, just because it fit in my hardware. But if you want to add more hardware, you could absolutely just add more clock checking and more turbo checking. Yeah, so that is what the design. Those are the 8 states for the design. As you can see here, we have that. Let me make that bigger for y'all. We have that table, or the picture. So we go from S0 to S2. S0 to S1 to S2 to S4 to S3, and then to S5, S6, S7, and then back to 0. And at any time, if V and L are both equal to 0, we move back to S0. And anytime we're in S1, if L is equal to 1 and V is equal to 0, we just keep repeating S1. and S3 is the exact same, not the exact same way, sorry, S3 acts like S1, but then moves on to S5. So those are kind of the differences between the two. But they have the same outputs. Everything else here besides S0, S1, S3 all have an output of F equals 1. So that's just, oh, and S7, sorry. So S2, S4, S5, and S6 have outputs of F equaling 1. So we will see why that matters in a bit. Now, I know it's kind of hard to see. I can zoom in for this. This is our transition table. So over here, written in just plain text, we have all the states with their different inputs, and then here we have the binary equivalents with Q2, Q1, Q0, and also their inputs, and then their next states. And then using this, we found the flip-flops, what they had to be, and then their outputs at every single point. So in using this, we knew we needed to make a 5-variable K-map, because we had 3 present states and 2 inputs, so that's 5 variables. And then we needed about 8 total K-maps for just J2 for all like the outputs, but then that needs to be doubled because we have a 5-variable K-map, so it's 8 5-variable K-maps, but 16 4-variable K-maps, in which is a lot of work, but we have it all here. So I did this on Google Sheets. So here we have J2, J2, and then we have each different 4-variable K-map table with one of the variables being 0 and one of them equaling 1. And here in the bottom of every single table is the corresponding equation. And so we essentially use all these equations, as you can see here. And all these, by the way, all of these like boxes and color boxes are the groupings. So the colors go match with each other from box to box. So this blue group is grouped with this blue group over here. This green group is only grouped over here. So that's kind of how you can read this. Sorry if it's a little illegible. But that just was the best way I found to do it on Google Sheets. So yeah. So moving on. To build this, we needed ands, ors, nots, XNORs, and then just 3 JK flip-flops. So despite this not having to use any D flip-flops or whatnot, it actually was a bit more expensive to make just because of how much hardware it was. These equations are a lot bigger. These Fs, especially the F and R, are a lot bigger than the equations for design 1. But I went with this because it had a lot more functionality to it, and it actually used the rest of the leftover states that the design 1 didn't use in the second JK flip-flop. And I chose the JK flip-flops as well because, yes, they are more math and more complicated, but they made it so that my equations could be smaller, and so I didn't have as many logic gates in the end. And here's my criteria. But yeah, so let's move on to the actual design in digital. So, oh. So this is the design in digital, as seen here. Essentially, the way that this is formatted is we have our V and L inputs over here with a L, L naught, V naught, and V all tunneled. And then here's our combinational logic. So this entire column is all the combinational logic with each one ending in a specific tunnel for J2, K2, K1. Some of them are missing because, especially for like J1 here was just equal to V. So I just routed V directly into it. I didn't bother even putting it in here just because it made it less circuits or less less hardware. Yeah. So here we have the combinational logic array. These are the flip-flops, the flip-flop array. I tied clear and set to ground as I didn't find a need for them in my design. Not that they couldn't be incorporated, but I just found that adding any extra hardware was inefficient for what I wanted to accomplish. I definitely could have, but once again, I thought it was inefficient. We also have our input for our clock, which is controlled by the user, but obviously you can program something to control it. And those are all tied together at the same clock. At the same clock. And then on the far right end, we have our outputs F and R, which are once again their tunnels align here. And these are definitely the biggest combinational logic because their equations were quite large. But yeah, so let me show this to you running in its glory. So here we have that S0 state. So when V and L are off, essentially, we have a state of nothing, so F and R will also be off. Now, just moving through the order of the states that I showed, we have um, we have L being on, and R immediately turns on because we originally my first design I had datas, sorry not data, I had data flip-flops, as opposed to just routing R and F directly, due to not wanting glitches in my system. But after talking with stakeholders, I realized it was unnecessary hardware to incorporate, as we simply don't care about glitches in a design like this. It's not really an issue if there is slight interference in the signal, because it won't really impact the output of the pumps in a significant way. So I foregoed those. So these are going to immediately update without a clock tick. But yeah, so when L turns on, R turns on, and no matter how many times I click this clock, R will never turn off, unless L is off, which then once again it does. It goes back to 0. So once we have L on, that's S1. That's our S1. And then our S2 is if V and L or V and L are off. If V and L are 1, or as long as V is 1, S2 will happen, which it does. As you can see here, S2 happens where we have the 1, 0, with F being on and R being off. And here is where the clock states matter. So once we have F on, F will be asserted for only 2 clocks. So as you can see, F turns off after 2 clocks. And once F turns off, instead of turning off the entire circuit, we have that for at least 1 clock cycle. So we're in S3 now. So we have that 1 clock cycle where S3 acts like S1. But if we do 1 more clock cycle, it's going to go to turbo mode. Because the pool is going to sense that, because we have V still being 1. So the pool is going to sense that, hey, we still need to fill this thing up with water. We need to do it fast. So after this 1 clock cycle, boom, both turn on, and F and R are going to be firing in turbo mode for about 2 clock cycles. So another one, and boom, and now we're in S7. So S7 turns both of them off, even though V and L, as you can see here, are both still on, it turns both off. And so yeah, so that is our design. And if we ever, by the way, if we ever have L back on, as you can see, R comes back on immediately. So if essentially what's happening is, if after turbo mode, and actually I can show you, so if we reclock this, so if I go into turbo mode, oh, I need to turn both on. So I'm in turbo mode here. If I ever turn V off and then clock it, as you can see immediately, R turns back on. So that was one of the things I had in my state diagram, where I wanted every single, like S5, S6, both route to S1 if V ever turns off. Because if you have turbo mode and turbo mode is working, what should happen is V will eventually turn off and just L will be left. And then you don't need turbo mode to fill up L. L can just fill up L by itself, because that was never a problem. What our restriction was with V and F. F cannot be on for more than 2 clock cycles of V. So we had to have a workaround, and turbo mode is our workaround for that. And then, yeah, and then that failsafe happens once again. If we just keep doing this, and then boom, that failsafe will happen, and the entire system will stop. And at any time, if you ever go to 0, 0, this will automatically just run you down back to 0, 0 at any time, no matter the clock speed. So that's another great thing about this, is that no matter where you are in the signal, even in turbo mode, if you turn both off, you're gone. And actually, if you turn L off too, as you saw, L must be on in order for turbo mode to be on, due to the fact that if your V is on, L must also be on. That was an assumption I made, because if the pool is very low, your other sensor is also going to be very low, unless the sensors are broken. So if V is ever on and L is not, then your sensor is broken. V should not be on. And that was an assumption I made, and so that is just another failsafe. So this also checks, is V working properly? If not, then we're just not going to run it. It will just never run. And so yeah. So that was the design. That is the Capstone, the working winning model. Thank you very much for teaching me everything I know, and thank you.